Okay, so today we are going to begin Chapter 7, Statistics. Woo! Yeah, so much fun. Okay, well, all joking aside, statistics is actually a very important area of math. In terms of how widely it's applied, it's probably the most useful topic in math that you will ever learn, right? There's a tons of math where people are like, what am I going to use this in my life? Why do I need to know calculus? Why do I need to know this? And to some extent that is actually true. I mean, there are some things in calculus like, if you're not an engineer, you won't need to know it. If you're not a math person or a physicist, you won't need to know it. Right? That's true for a lot of the math that you're doing. Statistics is actually quite different though. It's sort of the thing that is applied anywhere. Pretty much anything you're doing, being good at statistics and being able to get statistics on that thing is actually to your benefit, and no matter what, right? So, I mean, you're on your own store where you sell like, I don't know, Barbie dolls or whatever, you might think, well, the only math I need is arithmetic, I just need to know this is what I'm charging, you pay me this much, I give you this much change, I need to know what add and subtract, that's it. Well, what if you wanted to grow your business more? You'd need to know, well, which Barbie dolls sell the most? What time of the year do they sell the most, right? What kind of people buy these kinds of Barbie dolls, right? So you can sort of target your ads and things like that. You want to answer bigger questions. Statistics is the math that helps you to do that, no matter what field you're in, right? So, unfortunately though, statistics is usually taught in a very dry manner. I know it was when I learned it. So, I want to at least attempt to give you some idea of where it comes from and why we need it and where all this stuff comes from, because it's one of those things where you just have a lot of forms and you just do this form to do that and do this form to do that. But why? Why do we even care about these forms? Right? I sort of want to build up statistics from that point of view, and so it might take me a while to get to some of the familiar formulas but I think it's worth developing it in this way. So we're sort of I'm going to give you some definitions to start out, but then we're sort of going to analyze this situation and sort of see how statistics would arise naturally out of, wanting to answer certain questions. And then we'll eventually get to the familiar, the mean, the mode, the median, why do we even care about things like that, and so on and so forth. Let's go. We will focus on in chapter 7, right now, on what we call univariate data. This means we have a single variable that we want to measure statistics on, and each measurement, this will be made clear soon, is associated with one value. We'll also study soon bivariate data where we have two values, and when we get to that point I'll explain the difference. But for now we're going to be studying this, where we just have a single variable worry about, we're making one measurement and we're going to want to do statistics with that. Right? So what else do I want us to know? Well, how about what is statistics? Okay. So we have two basic definitions that we want to incorporate. This is the science of collecting displaying and analyzing data. Data is just some information that we know, set of facts or quantities or measurements that we take at some point. They can be numerical, they don't have to be, but often they are. Two, it can actually be the actual data. Displayed, analyzed. So So it can be described as a science, or it can actually be a noun, like baseball statistics. When you say baseball statistics, you're actually referring to the numbers themselves, right? So that's the basic definition of statistics. We're going to see why we care soon. Definition, when you say descriptive statistics, the focus of this chapter, refers to, what do we want? The science of quantitatively. Right? Remember we discussed the difference between qualitative and quantitative before, describing similar features of a set of data. Okay. What's the point? Big questions are the ones that matter to us in everyday life, right? So, normally if you're walking around in everyday life, a question that you'll encounter is, oh, what's the derivative of x cubed? Like, right? You're walking around everyday life, that will hardly be a question that you'd need to answer. We're talking about big questions, questions that matter to your life. Example, is smoking bad for you? Right? Lots of people smoke. You might wonder, oh, well, I noticed that this person over here smokes, he gets all these illnesses that this person over here tends to not get. Is it directly related to smoking or something else? Is smoking bad for you? That could be a question. It's a question that is applicable to your life, right? It's not like some abstract calculus or anything. This has to do with how you're living your life and certain questions that you want to be able to answer, right? Statistics is the math that helps us answer these questions, right? So, or get to some idea of what the answer would look like. So it's something like, I was living in a city, decrease lifespan. Maybe if you are, you're living in a city and you care about living long, you might want to think of moving. And you might think, will that actually help me live longer, right? Things like that. Right, so at the surface of it, they don't seem like math questions, but technically they really are. That might be a question on your minds. The students actually perform better in Jhevon's classes. Is it worth going through all these quizzes and tests and constantly being in fear for my life and my grade? Okay. So basically in life, there are these big questions that we want to be able to answer. And how we tend to answer them, especially to apply math towards answering them, statistics is the answer. Right? So let's analyze some data. So you can get the gist of where this is going. Something familiar to you. You have a class of 13 students, you know their grades, right? So the grades are F, A, B, B, C, D, C, C, F, A, B, C, D, F. Right? These are 13 grades. Okay.
Is that accurate representation?
No, it's a random example. We have way more than 13 students in this class. Random example, right? Note, not ordered in any particular way. You don't know what names go with each grade or anything like that. It's not particularly displayed in any useful way. Right? You can't really answer any questions you'd want to ask. You can't readily answer questions you'd want to ask. Right? For example, you have a list of grades. What are some questions you'd want to know the answer to?
The average grade.
What's the average grade? How many people got A's? How many people got B's? How many people got C's? How many people passed, right? If I'm just giving you a list of grades, and this is just 13, imagine I have like a jumbo-sized bio class where there are 200 of them, right? How would I have to answer those questions? I'd literally have to count the number of A's, count the number of B's, and all that, right? So the idea is, here I have some data in the real world, and I want to be able to analyze them. I want to be able to ask the question and get the answer right away. How many people got A's? How many people passed this class? You know, should something change, or should we stay the same, or things like that, right? These are the questions we want to ask, right? So, how many A's, how many passed? And by the way, average is something completely different. We're going to define this in a more statistics way. It doesn't always mean what you think it means. Right? So these are some questions we want to ask. But given just a random list of grades, it's actually hard to answer these questions. So your first thing, since you want to answer the question of how many, first thing you might want to do is throw these in a table. And give the frequency of each grade. Let me write out frequency since it's the first time I'm using that word. So I'd actually do that here. So I might say, okay, let's put these in a table. Grade. Let's make the frequency of the grade. The possible grades are A, B, C, D, and F. And now we go through the arduous process of finding out how many of there are each. 1, 2, 3. There are 3 A's.
3 B's.
1, 2, 3. There are 3 B's. 1, 2, 3, 4. There are 4 C's. 1, 2. There are 2 D's. 1, 2, 3. There are 3 F's. Now, at this point, the total. Did I? It's actually 15. I don't know. Why did I write my 5 to look like a 3 somewhere? Okay. Yeah, it's actually 15. Did we actually get 15 over
Yes.
here? That's 9 and 6. Yes, the total is 15 grades. Right? So I'm analyzing the grades of 15 students. Right? Now, look at the difference between the data displayed like this and the data displayed like this. If I gave one person the data in this form and another person data in that form, and I asked, how many A's? Who could be able to answer me faster? Well, the person with this table. Oh, there are 3 A's. How many C's? There are 4 C's. How many people pass? Pass is, I can define to be C or higher, right? Then I have to add those grades for C or higher, right? Which gives me another thing that we might want to add. So here I can ask how many A's, example. Right? And I can answer right away There are 3. 3 out of 15 students got A's. By the way, this is called frequency table. It helps us to answer the how many question. So you have this data, you want to be able to answer some questions about it, it's better to put it in a nicer form. How about a table where I can tell you the frequency of each data point that shows up? Now you might want to ask, how many got C or higher? Right? That might be a question that you're interested in. The answer is given by what we call cumulative frequency. This is just the frequency up to a certain point, all frequencies. So for example, I can go back here, grade, I can have frequency, and I can have cumulative frequency. So again, A, B, C, D, F. I have 3, 3, 4, 2, 3. Now what cumulative frequency does, yes? Do you have a
Do
question?
you know why in the rubric why they skipped the E and just went straight to F? Like it's A, B, C, D, F. Why did they skip the E?
All it means fail.
Do you know why?
That's just me.
I don't know. There are some grading systems that use everything. Like, I mean, when I was in high school, we even had E grades. But it's a grading system. They can choose how they want to grade you, right? Some systems will also have A pluses, A minuses, B pluses, B minus. This is just an example. I'm assuming these are the possible grades. It's just one of those things. Basically, if you really don't care if someone performs worse than a D, then you consider everything below that just a fail, and you just give that. It's up to you. We're pretending we have a system where these are the possible grades, and now I want to analyze this data that I have. Cumulative frequency works in the following way. You sort of add everything from that point and above. So when you get to B, you get 3 data points here, but before you had 3, so what you do is you add them together, so you get 6. And then to get to this one, you take that 3 and the 3 that you had before, and now you add 4, so at this point you have 10. Here, you get that 3 and the 3 and the 4, and now you're adding 2. That gives you 12. And here you have that 3, 3, 4, 2, and now you're adding 3. That gives you 15. And why would we care about cumulative frequency? Because it tells you about this point and everyone before. So now I can ask the question, how many people got C or better? 10, right? I don't have to go adding things. There's a column in this table that tells me the answer right away, right? So, 10 people got C. Be able to answer that question by defining what we call the cumulative frequency, which is just the frequency of everything at that point and before, right? So we can know how many people are at that level or higher, right? Another question we want to be able to answer. So here we have this list of data. We want to answer some average questions about it. Average, pun not intended. And we decide, oh, putting in a table allows us to answer this even easier. And then we might want to answer some other question, how many got C's or higher, and then we're like, okay, we need another piece of data. Maybe create something called the cumulative frequency, which tells us everything about that level and higher. Right? So now we can answer more questions about this data. And another question. What if we're talking about proportion? Percentage. you want to know if you're in this particular class or you want to join the class for this particular professor, what are your chances of getting an A? Right? On average, how many people get A's? Right? That might be a question you want to answer. How do you think we'd answer it?
Divide your grade by the total.
Right, divide how many people got it by the total number of people. That tells you the proportion of people. This is called the relative frequency. Answer is given by what we call the relative frequency. So this is just the frequency divided by the total, right? Which gives you the proportion, right? So I can have grades. I can have the frequency. I can have the relative frequency. I can have the cumulative frequency. Possible grades, A, B, C, D, and F. I had 3 A's, 3 B's, 4 C's, 2 D's, 3 F's. Cumulative frequencies were 3, 6, 10, 12, 15. Put a line here for total. So relative frequency, we care about the proportion. 3 people out of 15 people, which is the total, got A's. What percentage is that? Actually completed this before. This is 20%. 3 people out of 15 got B's. That's another 20% of the class. 4 people out of 15 got D's. This is 26.67% roughly. 2 out of 15. This is 13.33% roughly. F's 3 out of 15. This is 20% roughly. Now the sum of the relative frequencies should give you the total proportion, which is 1 or 100%. Let me just make a note of that here. It's okay to not get exactly 100%. Maybe sometimes you might round things and so the decimals won't add up to 100%. But in theory, it should give you everything. So 20% of students got A's. And there are a whole, that's not a question, that's actually an answer. And there are a whole bunch of things you can analyze the data. So here you can say, well, my chances of getting an A, a B, or failing are pretty much the same in this particular class, right? My chance of getting a C is roughly 26.67%, slightly higher than my chance of getting an A or a B, right? D is the one I have least chance of getting, right? So from this table, I get more information about this set of data, right? I can answer how many people got any given grade, how many people got any given grade or higher, and I can tell you what the chances are of getting any given grade, right? So just by throwing this in a table and displaying it, right? Statistics is about displaying and analyzing data. The way you display it can give you a lot of information, and you can answer questions really quickly about this information, right? When it wasn't, faster than you could if it wasn't displayed in a very accessible way. So this is sort of where statistics all begins, this idea that we want to be able to answer these questions about this data. How can we make our lives as convenient as possible? People think of statistics and they think of all these huge formulas. They don't really think of convenience. Oh, it's very convenient for me to compute the standard deviation. Yeah, but it is actually convenient. in some sense. Right? Here, I can conveniently answer these questions pretty quickly. Well, we won't go really further with tables here. Now we have a new problem with this organization, right? Which, if you went through statistics, you realize that this actually can happen to you. Tables can get too big, right? So imagine I don't just have like 5 data points, I have 1,000, 10,000, right? I'm doing this wide study of like 10,000 people. Now I have this table with 10,000 rows, right? It sort of gets annoying to answer questions. I have like all these numbers all over the place. It can get tiresome. So how do we fix that? Well, charts and graphs. Right? This is a pictorial way to represent your data, and sometimes that's all you need. Sometimes you don't care about the exact number, you just want to know things like, where are most of the data points, you know? And you can, looking at a picture, you can tell right away, as opposed to looking at a table with 10,000 rows, you have to search where the biggest number is, right? With something like a chart, it might be a lot easier for you. So some example of charts that we could use to display this data. Bar chart. Notice that we use this for qualitative data. For quantitative data, we'd use histograms. This is used for qualitative data. So for example, you plot category versus, it's usually relative frequency, but it can be any kind of frequency. Depends on what you care about the most, usually. So for example, let's look at this data set here in a table, in a bar graph. So I will put relative frequency on this. Relative frequency. And here I will put the grades A, B, C, D, F. And I'm going to do this here. 0.13, here 2. Okay, so my A's were 20% of the time I could get an A. B was the same. C, I had a higher chance. D, I had less if I had same as A and B. So now let's say the question is you wanted to know, you don't particularly care about the numbers, you can get them if you want from a frequency table, but let's say you just want to know what was the grade that most students got in this class? Right away you can see C, right? Instead of looking up at the table and looking for all the numbers and checking which number is the biggest, you can just see from this picture, C, right? You can see that the same number of people who got A's also got B's, and the same number got F's. You can tell that D is the least most popular grade in this class, right? You can sort of see how they relate to each other in terms of size, right? And you can see it like right away. You don't have to look up numbers in the table and see which number is the biggest, right? So if you just want to answer questions like, what is the most frequent grade? A chart is a good way to actually get that information. You can draw a picture and you don't have to look up into a chart of numbers. By the way, at this point, I should mention some things about charts. You're expected to be able to do these things without being asked specifically. A good chart has a title. It also has, a good chart will also have axis labels. So that's something like this, telling you what you're measuring, grade versus the relative frequency of grades. What else do I want? Well, something like a legend if it's too many. Legend. If applicable. In univariate data, you usually don't need a legend. But if there are many different kinds of data that you're doing, you might want to differentiate them. So if you have more than one data type. In this case, we only have one. We have grades, so we don't really need a legend. But a good chart would, in general, have these three components. You need to know what is the chart you're looking at talking about, and you need to know which one is versus which one. And if there are different kinds of data, you should be able to differentiate this by looking at the chart right away. Everyone okay so far, right? You see where we're going and why we're building this stuff. So the beginning we're given just a list of grades. Not very useful to answer questions, so we put it in a table. We can answer questions about how many. Then we throw in more columns to be able to answer what proportion, how many has this level or higher. And then sometimes the table gets too big, so we use pictures where you can just point at the answer. You can see it right away, right? And you need to know what your chart is showing. So you have that thing happening. We'll be getting to things like mean, mode, and median soon, like why those arise, but let's talk about some other kinds of charts. And many more kinds of charts that are important. One thing I want you to note about a bar graph is there are spaces between the bars. Just a convention. There's no real reason why there has to be. It's been decided that that's how we do. Example, histograms. Very important. It's basically a bar chart for quantitative data. So it's not like names, it's actually numbers, right? So let's look at grades again. So, example, let's say you have this list of grades. There are a lot. 1, 2, 3, 4, 5, 6, 7, 62, 51, 72, 78, 85, 87, 3, 82, 77, 54, 61, 62, 69, 81, 93, 92, 65, 70, 68. There are 20 grades in total. Right, 3, 6 is 18, and then we have 2. So that's 20 grades in total. And we're going to group these by what we call bins, right? This is just referring to intervals of data, right? It's not really going to be beneficial for me to put a whole bar for 57 and then 62 and then 51. Because then in a typical grading system, you'd have 100 bars. We don't really want that. Remember, we want to be convenient. So what I can do is I can group things that I think are important to be able to answer. So usually numerical grades have a letter equivalent. And a range of grades actually work in this equivalent, so let's actually do that. Sometimes you don't care about single data points, but you care about groups. Let's say I cared about all grades that are greater than or equal to 50 but less than 60. And then all ones that are equal to 60 but less than 70. Greater than or equal to 60, less than 70, or greater than or equal to 70, but less than 80, or greater than or equal to 80, but less than 90, greater than or equal to 90, less than 100, or up to 100. Right? Maybe that's the last endpoint you want. Right? These things are called bins. Right? Like intervals that you can throw your numbers into. They collect a bunch of numbers. So you have the grade, and we can do as before, frequency, relative frequency. So I'm given this list of grades. I want to be able to organize it so I can answer questions really quickly about it, right? So now let's actually throw them into bins. How many grades from this list are between 50 and 60, inclusive of 50? Well, you count them, right? 1, 2, 3, and that's it, right? So we have 3 grades that fall in this range from that list. And then we go and we count again. Between 60 and 70, 1, 2, 3, 4, 5, 6. How many between 70 and 80? 1, 2, 3, 4, 5. 5 between 70 and 80. Between 80 and 90. 1, 2, 3, 4. 4 between 80 and 90. Between 90 and 100. 1, 2. 2. Now this total should give us, right, that's 10, that's another 10, so that's 20. That should be the right distribution. 6, 5, 4, 2, yes. Okay, what about relative frequency? Well, I compute 3 out of 20, here I compute 6 out of 20, here I compute 5 out of 20, here I compute 4 out of 20, here I compute 2 out of 20. And I can write these as decimals or percentages. In this case, I wrote them as decimals. 0.15, 0.3, 0.25, 0.2, 0.1, adds up to 1. This is equivalent to 15%, 30%, 25%, 20%, 10%. So that's another way we can represent data in a table, but now let's say we want the picture. Because our data points are, yes?
Why are the bins from 50 to 60 instead of 50 to 59?
Well, it would be 59 inclusive, right? It's because I have an open bracket as opposed to a closed bracket.
Okay, oh, so it can't include 60.
It cannot include 60. Like if the data point is 60, I throw it in here. So this goes up to 59 point whatever, as long as it's less than 60. And often your bins, it's just what you care about. I could have done this differently. I could have said 45 to 55, 55 to 65, and whatever. It's just what we think of as important. But we decide to measure grades by these ranges, and so we just do that. And now we can get to a histogram. Histogram showing grade distribution again. So remember, it's just like a bar chart, really. But so now 50 to 60, 60 to 70, 70 to 80, 80 to 90. 90 to 100. And I want my relative frequency, so 1, 2, 1.5, 0.2, 0.25, 0.3. These are my bins. Relative frequency. So 50 to 60, what do we have? 15%. 60 to 70, we have 30%. 70 to 80, we have 25%. 80 to 90, we have 20%. 90 to 100, we have 10%. Notice no space between the bars. Also notice increasing order is how you list the numbers. Right, these are, yes, Dominique? No, not always. It's very typical though. You might graph it against frequency, but usually it's some sort of frequency. Relative frequency is the most typical one it's graphed against. So if someone just tells you, oh, graph a histogram, and they never really told you, you would assume that they want relative frequencies. It's the most typical one that we care about. So here we have a list of grades Not very useful as far as being able to answer questions from, but I throw it in this table and I can answer a lot of questions very specifically down to the number, to the second decimal place. But then if all I care about who's more than who, this picture would actually give me a lot more information. If I just want to know what grade range do most students fall in, 60 to 70, right? Instead of having to look at these decimals and realize, oh, this one is the biggest. You just say 60 to 70. Second most popular grade range is 70 to 80. Notice that getting 90 or above is the least likely scenario for this particular class in this example. But it allows us to answer a lot of questions about the data that we're looking at. So here I had this situation where we look like this. Now you can get a different kind of chart if you say, you put a dot at the middle of each bar at the top, and you connected them with lines. And you connected the bars. That gives you a chart that looks like this. This kind of chart is called a line graph. Another very popular graph. So these are the graphs usually used to measure trends. And so if you're into the stock market, you see how they measure stocks. They'd use this type of graph to measure it. It's where they want to see trends, as opposed to how much of something is going on. So it usually has time as the axis here, so you can see over time what's happening to this thing. You'd usually use a line graph, right? So it's usually used to do this. If you want to measure trends, you tend to use a line graph. If you just want to talk about frequency with numerical data, you'd use a histogram. If you want to talk about frequency with qualitative data, you'd use a bar graph. Right? Different charts are used for different reasons. That's sort of what I want to get to. And so this gives rise to the shape. So we want to analyze data. Let's analyze the shapes that can happen. I'm not going to talk about it too much here. For example, one type is called symmetric. Right? This means it's mirror image. About a central point. So for example, a graph like that. This you call it symmetric about A. While a graph like this is not symmetric about anything. you'll see symmetry actually plays an important role. When we'll get to averages, we'll see that a lot more often. Symmetric graphs are really nice because we can do a lot of predictions about them. And there's a very important symmetric graph called the normal curve, the normal distribution curve, which, especially as a bio major, you're going to be using that all the time. Which basically allows us to approximate any symmetric set of data. We can sort of pretend it behaves like a normal curve, and what we know about the normal curve, which is a lot, we can apply to this new set of data and make a lot of predictions about it. So shape is something important we'll come back to, but just to understand where this idea sort of comes from, you graph this line and then you look at how this line shapes. It can actually give you a lot of information. Let's see. Notice anything about this line graph? What's something that stands out to you? Someone said it. It has a peak. There seems to be a part on this graph that seems higher than every other point. And that's probably something we should care about. Depends on the question you want to answer, but it's a defining feature of this graph. Right? Now remember, we want to analyze data, try to answer all these questions. So data is given to us, or we collect it in the real world. It's in some unusable form. You try to organize it so you can answer questions. So you might start by throwing it in a table so you can tell how many of something. You put in cumulative frequency so you can tell how everything behaves at one point or higher. And then you can put in relative frequency so you can see proportions. But eventually your table gets too long, especially if you're collecting a lot of data points, so you start to use pictures. And when you start to use pictures, you start to notice these patterns. Hey, there's a peak here. Right? What does that mean, that there's a peak here? Right? And so you start to notice how things shape, and you're trying to figure out, okay, what does this mean for my data? Well, the important thing here is, especially if there's a peak, what that will suggest to you is there seems to be a so-called typical value. What's the value that most data points take on, right? What is the grade that most students get in this class, right? It seems to be, it's typical to have this, right? You'll notice in this class, it seemed typical to have a grade between 60 and 70, right? And it turns out the answer to a lot of our questions lie in the typical, right? So if I want to answer the question, for example, is smoking bad for you? Right? Or more specifically, does smoking cause lung cancer? What do? Follow 10,000 people who smoke every day and follow 10,000 other people who don't smoke every day. And then I check on them in 10 years and say, how many people have lung cancer among these two groups? And then if I might realize, oh, there's a peak happening here at the people who smoke. Maybe smoking causes lung cancer, you know? Or some sort of, you know, the people where the peak happens, or is the typical value. How many people who smoke will get lung cancer? You can plot it against percentages. Yeah.
The typical value of our average.
The typical value is going to be the average. That's what we're going to talk about next. I was trying to segue my way into it. Thanks for stealing my thunder. All right. This leads to what we call central tendency. And the so-called average. So we can see, on average, you know, a lot of people who smoke get lung cancer, right? So you can see that from your picture, right? So you're sort of want to say, you know, how likely is it for this to happen, right? That's the kind of thing we want, the average. Central tendency refers to the tendency of data to cluster around a certain point. Called the central value. So we're trying to analyze our data. What are the patterns that we see? Oh, here's a peak. It seems like most things fall in that category, right? It seems that the data tends towards to cluster around this point. So that's probably where our answers are, right? Because most people this happens to. That's probably where we'll find the answers to our question. So let's try to figure out this point that everything is tending towards. An average is a measure of central tendency. That is, it approximates this value that everyone's clustering around. So a lot of times for a lot of different kinds of data, you'll realize you start doing your statistics and it will seem like a lot of data points are going in this area. What is the most typical value of these data points? How do you approximate where most things will lie, right? The whole question of the average is try to approximate this value, right? So you have data, it was very unusable. You throw it into a table to make it more usable. Eventually your table gets too big, so you do pictures. Now when you see a picture, you see patterns, and now you start to see, oh, things seem to be clustering around this point. That's probably an important point to know. How do we get it? Well, we compute an average. It's just a way to figure out what is the most typical value. Right? Average is just an approximation for the typical value. And there are many different kinds of averages. A lot of people only think about one kind, which is the mean average, but average is actually much broader than that. Because this is what it's about, measuring where things tend to be. Right? So we'll talk about some common averages and when it's best to use them. One is the so-called the mean average. It's the one most people think about. And why? Well, it turns out that complex systems, well, let me tell you why it's most useful for symmetric data. Data clusters around the center value. And this is sort of the average that most people think of because it just so happens we live in a universe where most statistics ends up behaving this way. It's usually the most typical behavior. Complex systems, when you collect data from them, they usually cluster around a middle value somewhere, right? Pretty much anything to deal with human beings or anything that has a lot of complex characteristics will behave this way. You measure the heights of all people. It'll all average around some value, and it'll always be, most people are this height, but you have a few people are a lot taller and a few people are a lot shorter. But you'll usually have a range of heights where most of the human population will fall into, right? Usually anything you're doing with human beings will follow this data, this sort of shape. And so that's why usually when you say, oh, find the average, most people think, oh, add them all together, divide by the number of numbers, right? It's because it's the typical one, but it's not always the right one to use, but it's the one that most people think about. The mean equals sum of data points divided by the number of data points. And this idea sort of gets you towards the center. You'll notice if you take the average of two numbers, it actually gives you the number right in the middle, right? So if you take the mean average of two numbers. So this sort of gets you to what point is mostly in the middle of all values being considered. That is the mean. So if x1, x2, xn are data values, the mean would be equal to x1 plus x2 plus xn all over n. Right? And whatever number that gives you is called the mean average, meaning it's the most typical value for data that is symmetric. So, I'll talk more about this in a bit, but you might notice that if you're, for example, looking up salaries in a certain company, you want to know, oh, I want to be a pediatrician. What is my typical salary? They usually won't tell you the mean average. They'll tell you the median. You know, there's a reason for that. It's because salaries do not behave like this. Salaries don't cluster around a central point. We'll talk more about that later, but whenever you have sort of symmetric data, the mean is usually the best average to use. It's the guy that sort of gives you who's in the middle. So, an example. And the mean for the data set. Well, 3, 2, 15, 12, 9, 8, 12, 6, 3, 2, 15, 12, 9, 8, 12, 6, 3. So answer. Just plug in the formula. The mean would be equal to, you add all the numbers, divide by the number of numbers there. How many do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I should compute this ahead of time. This was actually 8.2. So above all these values, if you try to find the number that's sort of in the middle ground, it's 8.2. So that's an example. Another one is the mode. The mode is the value or values that occur most frequently. It's actually rarely useful. It can be. And you have one or several super high peaks. So if you're plotting out the chart for your data, and it looks like, you know, all the data points are here, blah, 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 they're just going about, and then like a huge amount just fall into some space right there, right? If your picture looks like that, then the mode is probably your best bet as the typical value. It's clear that most people are over here, right? You can point, oh, like most people, it's so obvious. Most people are right there. So what is the typical value here? Well, whatever value that is, right? If I had to bet, you know, what category you'd fall in, I'd bet that one, right? So whenever you have a sort of case like that, the mode is actually the better average to compute. If I see a graph looks like this, I would not do the mean for the average, I do the mode. Because that is a better measure of the typical value. It's very rare when this happens, but it can happen. Example. For the above data set, the mode is equal to, what would the mode be for this data set? The one I had before. 12. It is the number that shows up more than any other number. For this particular data set, it's actually not a good measure of the average, but it is one way to measure the average, but it's usually best if it's like this, meaning if I had this list of data and I had 1,000 more 12s, 12 would clearly be the typical value. It's not really a good one to use here, but I just want you to see the example. Another one, the median. So it means you take your data points, you arrange them in order, either increasing or decreasing, doesn't really matter, but you put them in order, and you pick the guy exactly in the middle, right? If there are, this would depend on if you have an odd or even number of data points. If you have an odd number of data points, then the middle will just be one number, but if you have an even number of data points, there'll actually be two numbers in the middle. If there are two numbers in the middle, then you define the median equals the mean of these two. So let's talk about that. Maybe I should write that out more. If we have, I mentioned this, but it's probably good to write down. An odd number of data points median equals middle value arranged. Equals the mean of the two values. So, example for the above data set. I'm using the same data set we have over there. If I wanted to get to the median, the first thing I'd have to do is arrange these in some sort of order. Let's do ascending. How would I arrange these in ascending order? 2 is the smallest value. There are 2 3s. 6. There's an 8. 8. 9, 12, 12, 12, 15. Is that it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So now we start to try to figure out who is in the middle. You can do something elementary like just start crossing out people from the outsides. Cross out that, 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 cross out that. Boom. There are 2 numbers in the middle because I have an even number of data points. So my median equals the mean average of 8 and 9. So it's 8 plus 9 all over 2, which is 8.5. Outlier is a value much higher or much smaller than the other values. When would you use the median? Usually when you have like outliers. So for example, salaries in a media corporation. Now if you're graphing the salary scale, you want to say, oh, you know, if I start working for this company, what would my typical salary be? Well, salaries are distributed sort of weird. You have, you know, all your entry-level workers down here. You know, it goes, you know, your salary gets a little higher if you're, you know, like senior staff. You know, and oh, it gets a little higher if you're like, you know, executives and stuff like that. Right? So your salary might be here. At entry level, you make like 30,000. After a few years, 40 to 50,000. The executives would make. Position. And salary. Then CEOs, presidents, etc. would be making like the big money, millions, right? So this guy might be making, you know, roughly 30,000 just for example's sake, right? This guy over here is like making 50 million a year, right? Well, the little guy down here is making 30,000 per year. Now, it turns out, relatively speaking, there are not a lot of CEOs. A company might have 1, 2. There's like 1 person making all this money. Down here, you have a bunch of people making relatively a little bit of money. If you were to take the mean average, you know, it would actually skew it to the right. Like, when you take an average, You add up all these little numbers, but then you add this huge number. So now when you divide by the number of numbers there are, you will get something closer to over here, right? The mean would be like over here. And so if you take the mean average, oh wow, I can make all this money by working at this company. Wow, right? If they tell you the mean salary, the CEO's salary is going to push it up. So it's not a very good salary to take, right? While the mode, well, again, the mode would sort of be in the entry level, right? You have a lot of people just down at the basic trying to get the grunt work done, all the secretaries, the receptionists. You have more of them than you have executives. So if you look at that, you're like, holy crap, I'll only make $30,000 a year. Also not a good measure of salary. But if you take the median, it sort of tells you, well, if you stick with this company long enough, you'll probably end up somewhere here, and that would be your typical salary. Right? So in the case of salary, this is why they tell you the median. Right? Right? If you're looking at the salaries for a certain profession, no one tells you the mean. Right? Because there's the fat cats up the top, we're going to push the mean up and give you an unrealistic expectation. Again, they're not going to tell you the mode, because you're usually going to get a salary where, you know, you've been working there a couple months, that would be your salary. Right? They tell you the median, right? If you stay in this company a few years, 5 years or so, this is what you should be expecting, right? So in the cases of salary, the median is the best average to use, and which is why it's what they always tell you. So again, just to bring it home, in the real world, we collect all this data, but it's not very usable. We can't answer questions, so we try to organize it. One of our first ways to organize it is to throw it in a table so we can tell how many of something there are. And then we can have more columns to answer more questions. You know, we can talk about relative frequency. What proportion of people get this? And we can talk about cumulative frequency. What proportion of people get this or better? And then eventually, if we're taking a lot of data points, the table gets too big and you can't be able to look up the numbers where the biggest ones are, so you draw pictures. Then when you start to draw pictures, you start to see patterns, and you start to see where most data tend to lie, if that's the case. And so you're going to want to be able to measure that point, right? And so an average is a measure of the typical value. And for different scenarios, you'd use different ones. The mean is the most popular one. It's the one most people know about because it's the one that usually shows up in nature. Nature is complex, and complex systems usually center around the central value. Not always the case, but very typically the case. That's why everyone thinks of the mean when you say average. But it's not really the only way to measure an average. Another thing that's important for us, variation. So we saw that there could be a typical value and we want to try to get to this. There are a bunch of ways we can get to it, the mean, the mode, the median. There are others. But there's something else that usually comes to light as well if you start to analyze data closely enough. This refers to how widely data points spread out. Is there anything you want to say? About the central line. Numerical value. Assigned. It's called the variance. So if you want to measure how data is spread out, and you put a number, a numerical value to that description, you call that number the variance. So you might be thinking, why is this important? Why do I care? Right? Isn't average good enough to analyze data as much as we need to? It turns out not. Consider these two. data sets. Here's the first data set, 4, 10, 16, 22, 28, 34, 40, set 2, 19, 20, 21, 22, 23, 24, 25. Okay, so that is our data set, 4, 10, 16, 22, 28, 34, 40, 19, 20, 21, 22, 23, 24, 25. Okay. So we got to the stage where we're looking at pictures and we want to talk about typical values. That's fine. We can address a lot of questions by doing this. But there's something even deeper if you start to look closely enough and you start to get experience with statistics and you're looking at like 2 data sets like this. What is the mean for the first set? If you compute, it's 22. What is the mean for the second set? It also is 22. What's the median for the first set? It's 22. What's the median for the second set? It's 22. Which means, as far as average goes, these 2 data sets, indistinguishable. I cannot tell the difference between these 2 set of numbers. If all I'm using is the average, that is. Right? But clearly, there is something very different about these 2 sets of numbers. Right? So, what do I do about that? Well, I talk about variation. The mode is not really useful. There's no one number that shows up any more than another one. So, basically in terms of the averages that I've been using, I can't tell the difference between these 2. But clearly there's a difference. Right? This is why we need variation. This is why it's important. Sometimes the average isn't good enough to analyze data and distinguish between different data sets. Right? So now we're going to talk about measures of variation. The first one important for us is called the range. And that's just the difference between the highest and lowest value. So, example. The range for set 1 would be 40 minus 4, which is 36. And the range for set 2, 25 minus 19 equals 6. Now we're starting to see a difference between our two data sets, right? So set 1 ranges over So right away, we see a difference between our two data sets that we couldn't see before if all we cared about was average. So that is very important for us to know. Allows us to tell the difference between certain things. But if you keep going further, even the range isn't good enough. Another problem. So sometimes average isn't enough, but sometimes range isn't enough as well. Example, consider these two data sets. (20, 66, 45, 70, 75, 100). Set 2, 20, 90, 95, 95, 88, 100. Think of these as grades. And note, the range for set 1 is equal to the range for set 2, which is equal to 100 minus 20, which is 80. So here I have two different data sets. Now I look at their ranges. It happens to be the same. But clearly, if you're trying to figure out, which class is performing better, there's actually a clear answer, right? This class is doing better. More people are getting 90s. There's like this one kid that's not studying, right? Well, over here, like half the class is hardly studying. Clearly, this class is performing better than this one, right? But they have the same range of grades, right? So sometimes the range doesn't distinguish enough either. And so we'll sort of, I'm going to get through that. Okay, we'll talk about next time how we get around that problem. Been a lot of definition, a lot of writing, enough writing for today. So basically this is sort of how statistics work. Basically we have a lot of data that we need to organize so we can answer questions. Throw it in a table. Tables get too big. We use pictures. We use pictures to find patterns. Patterns shows up, oh, there's a typical value. So we want to measure that. We get the average, right? We have mean, mode, median, right? Then we're like, there are cases where that doesn't give us enough information. So we develop variation and ranges. And sometimes the range is not enough, which is why we're going to develop things like interquartile range. We're going to have quartiles and box plots and then standard deviation and all that's coming up and why we need them. Okay? We'll pick up next time.